Welcome to Learn with us. This is the 27th lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you studied about bias point of junction field effect transistors, where you understood how you are going to establish bias point of JFET. In your previous lecture, you also understood midpoint bias and voltage divider bias of junction field effect transistors with the help of some examples. What are the learning objectives of this lecture? In this lecture, you will study about the second major classification of field effect transistors, which is metal oxide semiconductor field effect transistors. You will also study about different types of MOSFETs. In this lecture, you will also understand transfer characteristic curves of different types of MOSFETs. Now we will talk about metal oxide semiconductor field effect transistors or MOSFET. The MOSFET is different from junction field effect transistor. It has no p-n junction structure. The gate of the MOSFET is insulated from the channel by a silicon dioxide layer. The two basic types of MOSFETs are depletion type and enhancement type. Of these two types, the enhancement MOSFET is more widely used. The construction of the metal oxide semiconductor field effect transistors is very different to that of the junction field effect transistors. Both the depletion and enhancement type MOSFETs use an electrical field produced by a gate voltage to alter the flow of charge carriers, that is, electrons for n channel and holes for p channel through the semiconductive drain source channel. The gate electrode is placed on the top of a very thin insulating layer. Now look at this figure. As you can see here, this gate electrode is placed on this silicon dioxide layer, which is a very thin insulating layer here, and there are a pair of small n-type regions just under the drain and source electrodes. So this is the construction of an n-channel MOSFET here. We know that the gate of a junction field effect transistor must be biased in such a way as to reverse bias the p-n junction, but in case of MOSFET device, there is no such limitations. It means in MOSFETs, it is possible to bias the gate in either polarity positive or negative. Okay. Now we will understand depletion type MOSFET. The depletion type MOSFET requires the gate to source voltage to switch the device off. This depletion type MOSFET is equivalent to a normally closed switch. Now we will look at the symbol of D MOSFET. If you have a symbol like this. Okay, where this terminal is drain, here we have gate, and here we have source. And if arrow is here like this, then it is N channel D MOSFET. Now what about the symbol for a P channel D MOSFET? It is like this. Again, here we have gate, here we have drain, and here we have source. Okay, now here the arrow will be like this. Okay, so this is the symbol of P channel D MOSFET. Okay, in depletion type MOSFETs, for N channel, negative gate to source voltage is applied, which will deplete the conductive channel of its free electrons, switching the transistor off. It means there will be less electrons here. Likewise, for a P channel D MOSFET, positive gate to source voltage is applied, which will deplete the channel of its free holes, turning it off. It means there will be less holes here. In other words, for an N channel, when positive gate to source voltage is applied, there will be more electrons and more current, which will turn the transistor on. The opposite is also true for the P channel types. It means the device is normally switched on, or it is conducting without the application of gate bias voltage. It means the channel conducts when gate to source voltage is 0. Okay. Due to this reason, the depletion mode MOSFET is equivalent to a normally closed switch. Okay. Now we will understand transfer characteristic curves of depletion type MOSFETs. We know that for an N channel D MOSFET, negative gate to source voltage is applied. So the current voltage characteristic curve will be like this, where the variable of negative x-axis will be negative gate to source voltage, and the variable of y-axis will be drain current. Now here the curve will be like this. Okay. Now the point on this curve where VGS is 0, it means here it corresponds to IDSS, and the point on this curve where ID is 0, it means here it corresponds to cutoff voltage. Now, what about P-channel D MOSFET? We know that for a P-channel D MOSFET, positive gate to source voltage is applied. So the curve will be like this, where the variable of y-axis will be ID and the variable of x-axis will be positive gate to source voltage, and here this transfer characteristic curve will be like this again. At this point we have IDSS and here we have cutoff voltage. Now, just like junction field effect transistors in depletion type MOSFETs, cutoff voltage and pinch off voltage are equal in magnitude but opposite in sign. Okay, so these are transfer characteristic curves for an N channel and for a P channel MOSFETs. Now look at this example for a certain D-type MOSFET. If IDSS is 10 milliamperes and cutoff voltage is minus 8 volts. So first of all, is this an N channel or a P channel D MOSFET? Now, as you can see here, this cutoff voltage is negative. It means here the curve will be like this. Okay, this is minus 8 and here we have 10 milliamperes. It means it is an N channel D MOSFET. Okay, now if you want to calculate drain current when gate to source voltage is minus 3 volts, so how you are going to find this drain current? For this you will use this equation of drain current. Okay, 1 minus VGS divided by cutoff voltage whole square. Here we know that this IDSS is 10 milliamperes and here we have minus 3 volts gate to source voltage and this cutoff voltage is minus 8 volts and here we have whole square. Okay, after solving this you will get 3.91 milliamperes. So this is your drain current when gate to source voltage is minus 3 volts. Now if you want to calculate the value of drain current when gate to source voltage is plus 3 volts, okay, so what will you do now? again you will use this equation ID approximately equal to IDSS 1 minus gate to source voltage divided by cutoff voltage whole square. Okay, now we know that here this IDSS is 10 milliamperes and this gate to source voltage is 3 volts, and here we have minus 8 volts cutoff voltage. This is whole square. Now after solving this you will get 18.9 milliamperes. Okay, so this is your answer. Now look at this example. If you have a D MOSFET where IDSS is 18 milliamperes and cutoff voltage is plus 10 volts. Okay, now is this an N channel or a P channel D MOSFET? Now if we draw its transfer characteristic curve, it would be like this. Here we have 10 volts and here we have 18 milliamperes. Okay, it means here this cutoff voltage is positive, so it is a P channel D MOSFET. Now if you want to find the value of drain current when gate to source voltage is 4 volts, so what would you do? You will use this equation ID approximately equal to IDSS 1 minus gate to source voltage divided by cutoff voltage whole square. Now here this IDSS is 18 milliamperes and here we have 1 minus 4 divided by 10 whole square. After solving this you will get 6.48 milliamperes. Okay, to find drain current when gate to source voltage is minus 4 volts, again you will use this equation where ID is approximately equal to IDSS 1 minus VGS divided by cutoff voltage whole square. Here this IDSS is 18 milliamperes and here we have minus 4 divided by 10 whole square. Okay, after solving this you will get 35.28 milliamperes. So this is your answer. Okay, now we will talk about enhancement type MOSFET. The enhancement type MOSFET requires the gate to source voltage to switch the device on. The enhancement type MOSFET is equivalent to a normally open switch. Now we will look at the symbol for an N-channel E MOSFET. It is like this. Okay. Now this terminal is gate. This terminal is drain. Here we have source and here arrow is like this. So this is the symbol of an N-channel E MOSFET. Now what about the symbol of a P-channel E MOSFET? It is like this. Again, this terminal is gate. Here we have drain and here we have source. Now here arrow is like this. So this is the symbol of a P-channel E MOSFET. Okay. This E-type MOSFET is the more common type of MOSFET, which is the reverse of depletion type MOSFET. It means in this enhancement mode, the device is normally off or non-conducting when the gate bias voltage VGS is equal to 0. Now, for an N-channel E MOSFET, application of positive gate to source voltage will turn the transistor on, while application of negative gate to source voltage or 0 gate to source voltage will turn this transistor off. Therefore, this enhancement type MOSFET is equivalent to a normally open switch. The reverse is true for the P-channel MOSFET. It means when negative gate to source voltage is applied, then the device is on, but when positive gate to source voltage is applied, it will turn the transistor off. Okay, so this is the enhancement type MOSFET. Now we will understand the transfer characteristic curves of enhancement type MOSFETs. We know that in case of N-channel E MOSFET, positive gate to source voltage will turn the transistor on. So here the IV characteristic curve will be like this, where the variable of y-axis will be drain current and the variable of x-axis will be positive gate to source voltage, and here the curve will be like this. Now this point is threshold voltage. Now what about P-channel E MOSFET? As I have mentioned in my previous slide that negative gate to source voltage will turn the transistor on in case of P-channel E MOSFET. So here this curve will be like this, where the variable of y-axis will be drain current and the variable of x-axis will be minus gate to source voltage, and here the curve is like this, where at this point we have threshold voltage. Now as you can see, there is no drain current here when VGS is 0. It means these enhancement type MOSFETs does not have a significant IDSS parameter like junction field effect transistors and depletion type MOSFETs. Also note that there is ideally no drain current until gate to source voltage reaches a certain non-zero value called the threshold voltage. Okay, it means, as you can see here, there is no drain current until threshold voltage is reached. Okay, so these are the transfer characteristic curves for an N channel and a P channel E MOSFETs. The equation for the transfer characteristic curves of the enhancement type MOSFETs differs from that of the junction field effect transistors and the depletion type MOSFET because, as you saw in the previous slide, that the curve starts at threshold voltage rather than cutoff voltage on the horizontal axis, and it never intersects the vertical axis. So the equation for the enhancement type MOSFET transfer characteristic curve is ID is equal to K gate to source voltage minus threshold voltage whole square. Here this K is constant and its value depends on the particular MOSFET and it can be determined from the datasheet. Okay, and here if you have the values of gate to source voltage and threshold voltage, then you can find the value of drain current using this equation. Okay, now look at this example. If drain current is 500 milliamperes and gate to source voltage is 10 volts and threshold voltage is 1 volts, and if you want to find the value of drain current when gate to source voltage is 5 volts, so how you are going to start your analysis? First, you will find the value of K because we know that ID is equal to K gate to source voltage minus threshold voltage whole square. Okay, now if we rearrange this equation, we get K is equal to ID divided by gate to source voltage minus threshold voltage whole square. Now if we put these given values here, we know that ID is 500 milliamperes, gate to source voltage is 10 volts and threshold voltage is 1 volt, and here we have whole square. Okay, now after solving this you will get 6.17 milliamperes per whole square. Okay, so this is value of K. Now For finding drain current when gate to source voltage is 5 volts, we use this equation. ID is equal to K gate to source voltage minus threshold voltage whole square. Now we know the value of K, it is 6.17 milliamperes per whole square, and here this gate to source voltage is 5 volts now, and this threshold voltage is 1 volt, and here we have whole square. So after solving this, you will get 98.7 milliamperes. Okay, so this is your answer here. Now look at this example. The datasheet for an E-type MOSFET gives drain current 100 milliamperes, and here gate to source voltage is 8 volts and threshold voltage is 4 volts. Now if you want to find the value of drain current when gate to source voltage is 6 volts, so how you are going to start your analysis? Again, first you will find the value of K. For this you will use this equation. ID is equal to K multiplied by gate to source voltage minus threshold voltage whole square. If we rearrange this equation, we get K is equal to drain current divided by gate to source voltage minus threshold voltage whole square. Now if we put these values here, drain current is 100 milliamperes and gate to source voltage is 8 volts, threshold voltage is 4 volts, and we have to take their whole square. Okay, now after solving this, you will get 6.25 milliamperes per volt square. Okay, so this is the value of K here. Now for finding drain current when gate to source voltage is 6 volts, we use this equation. ID is equal to K gate to source voltage minus threshold voltage whole square. Here we know that this K is 6.25 milliamperes per volt square, and here this gate to source voltage is 6 volts now, and we know that threshold voltage is 4 volts, and we'll take their whole square. After solving this, you will get 25 milliamperes. Okay, so this is your answer here. We know that these are the symbols of depletion type MOSFET, and these are the symbols of enhancement type MOSFET. Now the line in the MOSFET symbol between the drain and source connections represents the transistor's semiconductive channel. If this channel line is a solid unbroken line, then it represents a depletion type MOSFET, as you can see here, as drain current can flow with zero gate biasing potential. Now if this channel line is shown as a dotted or broken line, as you can see here, then it represents an enhancement type MOSFET as zero drain current flows with zero gate potential. Now the direction of this arrow pointing to this channel line indicates whether the conductive channel is a p-type or an n-type semiconductor device. So these are the differences in symbols of D-type and E-type MOSFETs. That's all for today. Now what are the key takeaways of this lecture? In this lecture, you studied about MOSFETs, which is the second major classification of field effect transistors. You also studied about their construction and you understood how these MOSFETs are different from junction field effect transistors. In this lecture, you also studied about two basic types of MOSFETs. First is depletion type MOSFET and second is enhancement type MOSFET. You also studied about symbols of these two types of MOSFETs. In this lecture, you also understood transfer characteristic curves for an N-channel and P-channel depletion type and enhancement type MOSFETs.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.